the video lecture, I actually went through the derivations, but I also uploaded this Python notebook to the Brightspace. So I want to walk you through what this Python notebook does. So if you remember what the goal of the derivations is to solve the linear momentum balance, which is basically doing this integral. I'm gonna ignore the integrals of the body forces and the traction boundary conditions, so only looking at the stress. And then the integral of the stress double contracted with the variation of the velocity gradient. And you already know that you have given nodal positions for the reference and the deformed configuration. You should be able to calculate the deformation gradient f inside of the element using the shape functions. So this is what you did in a previous homework. And given that f, you could calculate the stress. So that should be done by now. And then the other one is that then we're going to introduce arbitrary variations. And based on this, we can compute we could compute this variation of the symmetric velocity gradient. And then we can take out the actual values of the variations outside of the integral. And then what we are left with is the stress with a gradient of shape functions. And then we have, for each shape functions, we have one entry, well, actually two entries. So we have, for each shape function, we have x component of this equation and a y component of this equation. So that's what we end up with. So we have done that before. So how to calculate the residual? Again, given the reference and deformed coordinates, you should be able now to calculate the deformation gradient. Given the deformation gradient, you can calculate the stress. Then on the other hand, if you plug in the discrete variation with the nodal variations delta UE, and you take these values outside of the integral, what you are left with here are going to be gradients of shape functions, and it's going to be a vector of 8 by 1 for the quadrilateral element, so twice the number of nodes. So that gives us the residual, which I didn't rewrite here. And then for the tangent, you know that I didn't do the derivation for the spatial configuration. I only did it for the reference configuration, but you end up with the stress double contracted with the gradient of the increment times the gradient of the variation, and the integral of the increment times c, which is the elasticity tensor for the spatial configuration, times this should not be the gradient of this should just be delta d, should not be, yeah, should just be like this. And then if you introduce here the corresponding variation as the sum of the shape functions times the nodal variations, and the increment as the sum of the shape functions times the increment, you can also take this variation and this increment, the nodal values, outside of the integrals in both integrals, and then what you're left with are going to be the definition of the stiffness matrix, of the elasticity, the tangent matrix, basically, this Ke. So I'm gonna illustrate that in a sec. For that, we need some constitutive model. This is a very, very simple constitutive model that we're gonna use, and this is the corresponding tangent. And in Voigt notation, this is how it looks like. And this is, if you just read the text, the alternative to doing these double products, double contractions with the fourth order elasticity tensor and this 2 second order tensor is to rewrite this in Voigt notation, and the C in Voigt notation in this case is just a 3 by 3 matrix, and this in Voigt notation is just a 3 by 1 vector, because we're doing everything in 2D. All right, so here I have my mesh, and this at the beginning I only have the deformed positions. So if you look at it, it's this mesh right here, And then what I do is the definition of shape functions. I'm gonna apply Dirichlet boundary conditions to all the boundary. So I'm not, because I don't want to deal with tractions on the boundary. I just want to have you being able to solve this problem for the Dirichlet problem. So completely define boundary conditions, non-displacements here. I'm gonna just deform it such that these two are gonna be fixed, but these two I'm gonna move to the right. So you can see that now I deformed my mesh. But obviously I didn't do anything to these nodes. These are the interior I just kept the same. I only moved the boundary. And the goal is to basically solve now the equilibrium problem to update the position of these inner nodes, and they should move to the center. So I have this function where I have compute the residual and the tangent. I put it into a function just because I need to use it in the Newton-Raphson loop. I initialize a total residual, which is the size of 2 times the number of nodes. And also the tangent, the total tangent is 2 times the number of nodes, times 2 times the number of nodes. And just remember that number will go down because not all the residuals are going to be 0. Actually, when I finish assembling the total residual and the total tangent, I need to take out of the residual only the part of the residual that corresponds to free nodes, so nodes that don't have essential boundary conditions, and then I need to remove also the corresponding rows and columns from the tangent. So conveniently, I have numbered my nodes such that the first 4 nodes, here, let's go here, you can see that the first 4 nodes are the nodes on the boundary. So that's just for convenience. You can't always do this, but for convenience here I have the first 4 nodes are the nodes on the boundary. So that's gonna come in handy because again, when I am doing here in this function, I'm going to assemble the total residual and the total tangent, which is 2 times the number of nodes in length. But again, not all the residuals are going to be 0. We know from when we were doing the weak form that whenever we have an essential boundary condition, then the residual is not going to be 0 because it's going to be equal actually to the unknown reaction forces. But because we have the weighting functions or the variations to be 0 at those nodes, then the product of the variation times the residual is 0, but the residual itself that we're going to calculate is not going to be 0. So at the end of the day, we have to split this total residual and this total tangent and get only the part that we need. Okay, how do we fill in this? We have a loop over elements. We initialize the residual of the element and the tangent of the element. That's just a vector 8 by 1 or a matrix 8 by 8. This you've done from your homework. Get the nodes that make up this element. Then the reference and deformed coordinates of this element. Fill that in with this for loop. And then we're going to have a loop over integration points. I'm doing the 4 integration points for the linear quadrilateral. These are my integration points. Evaluate the shape functions. Given the shape functions, evaluate the isoparametric map, so the interpolation of the capital X and the lowercase x. Also evaluate the Jacobians. I have 2 Jacobians. The Jacobian with respect to from the parent domain to the reference, so that's this, or the Jacobian from the parent domain to the deform, that is this. I can calculate, if I get the inverse transpose of each of these Jacobians, then I can calculate derivatives of the shape functions with respect to capital X, derivatives of the shape functions with respect to lowercase x. Then get the deformation gradient. So, it's like sum of dyadic product of the lowercase x times the derivative of shape functions with respect to capital X. Given the deformation gradient, compute the stress. And then now actually doing the residual. So for the residual, loop over nodes, because the residual is 8 by 1, and it's 8 by 1 because it's 4 nodes and each node has an x and a y component. So another way to loop over these 8 values is to have a loop over nodes, and inside of that a loop over coordinate, x or y. So loop over nodes, gonna initialize my variation, so this delta v with zeros, and then depending on the coordinate, I'm gonna make that to be a 1. So, and I don't have to worry about the fact that some of them are on the boundary and this variation should vanish, because what I'm gonna do is I'm gonna ignore that row of the residual anyway. So I don't have to adjust my variation to be 0 for the boundary. All right, so initialize the variation with zeros, then depending on if I'm looking at the x or the y component, make that to be non-zero. So 1, actually any number here would work. And then calculate the gradient of the velocity, or the virtual velocity, with respect to lowercase x. That's just the outer product of that variation times the gradient of the shape functions with respect to lowercase x. And here, note that I don't have a sum, because the variation that I'm thinking about should only be for the node ni. So only one node and one coordinate at a time. So I calculate my gradient of the variation, and then I calculate the symmetric velocity gradient, and then I can add to my residual. What do I add? I add the contraction of the stress with that symmetric variation of the symmetric velocity gradient. And then, this is related to the integration. So this is related to the Gauss integration. And then I can put that into the global residual. The only thing is the same thing on the right hand side. The only thing that changes is for the residual, it should be 2ni plus ci. So you can see that this will go from 0 to 7 because I have 8 entries. And this one is just the map from the local node ni to the global node node ei ni. So this is the global node number. That's it. So for the tangent, again, loop over nodes. So another loop over nodes, and then another loop over coordinates, but for the increment. Same procedure as before. I initialize my increment to be zeros, and then I'm just gonna make my the corresponding x or y component to be 1. Then I can get my gradient of that by the outer product of the increment times the gradient of the shape function, only the shape function and j. And then I can calculate my delta epsilon, so my increment of the strain, which is just the symmetric gradient. And then the tangent has 2 parts. We said one part, if you just scroll back to the definition, one part is the stress contracted with the transpose of the gradient of the increment times the gradient of the variation. So that this is the geometric tangent, and is the stress contracted with the gradient of the transpose of the gradient of the increment times the gradient of the variation. And then the other one, the material tangent, is in void notation, is a vector. So I need the increment of the strain, but in void notation, times this D matrix, which I gave here, times the variation, but in void notation, so a 3×1 vector. So if you come back here, you'll see I put the symmetric velocity gradient in void notation, so that just has 3 entries, and then it needs these 2 for the contraction to be accurate. And then I also put this delta epsilon or delta strain in this void notation. And then this is the D matrix that you can see above. And so the material tangent is the dot product of the delta epsilon So that's the increment of the strain times the matrix D times the void of the symmetric velocity gradient. And then add that to the corresponding entry of the element tangent. Again, need to add the part related to the integration. And then for the total tangent, just instead of ni, go to the global non-number, which is not ei ni. And for the j, same, from the local non-number to the global non-number. And then, yeah, this is the same as before. So that's it. And I can go over this more slowly in class. All right, so this is if you just need to redo. And so if you run the code, what does the Newton-Raphson code requires? You evaluate the residual and the tangent. You have your initial guess. Your initial guess, like I said, is I don't do anything to the internal nodes. Then I assemble residual and tangent. I only need, so I'm creating this RR-DOF and KK-DOF because I only need the ones that correspond to the nodes that do not have essential boundary conditions. So I ignore the first 8 components because for the first 4 nodes, I know their X and Y value. So in total, I know the first 8 entries of the residual are not going to be 0 because they have essential boundary conditions. So I need to ignore them. And then I also need to ignore the corresponding rows and columns of the stiffness matrix. And then I calculate the increment by doing the solution of the stiffness or the tangent times the residual. And then just note again that once I calculate that increment is for the nodes that do not have essential boundary conditions. Because the nodes that have essential boundary conditions, I know their position. So obviously this gives me, if you see the total number of nodes was 8, so the total residual was 16 by 1, but I'm ignoring the first 8 entries. And so this increment, when I solve this step, I get only a vector of 8 by 1, right? Because again, I don't need to update the position of the first 8 nodes because I already know it. So I only need to update the position of the second part of the nodes. So the second half of the nodes. So this is what I'm doing here. And that's it. So if you run the code, you will see the convergence. So, not exactly quadratic, but almost quadratic. And so, after 10 iterations, it should be smaller than our tolerance, which was 10 to the minus 5. And then if you plot it, you will see that basically you get a uniform stress and the inner nodes have moved to the center. So that's it. That is the solution. And yeah, I would suggest to very slowly go over the code and then compare to the formulation of the residual and the tangent. And again, the key point is that if you plug in the discrete variation and the discrete increment and you take out the nodal values and you're only left with the shape functions, that is the same as what I'm doing here, which is I'm looping over nodes and looping over the coordinate. And even though I'm making this variation to be 1, in reality, what I'm doing is basically isolating sort of the contribution of each of the nodal variations. So in effect, I am doing the same thing of taking the increments and the variations outside of the integral. I'm pretty much doing the same. But yeah, I would suggest to go over this slowly to see how this matches. This is the main code, like this. The rest, hopefully, from what we have done before in this previous homework, how to get F and from F get the stress. And I think maybe this is probably the part where I would suggest you spend most of your time to try to see if this makes sense, the way I'm assembling this residual and this tangent. And that's it. Then the Newton-Raphson, I think that should also be familiar, at least. to before. Maybe the only thing that might be a little bit unfamiliar is the fact that I have to split this residual and the tangent, because I need to ignore the ones that have essential boundary conditions, and then that also makes me update the increments just for certain nodes, not for all nodes. So, but this is a little bit more, I would say, programming technicality, whereas this one is a little bit more conceptual. So I would spend more time taking a look at this part of the code, making sure that this is completely clear. And I'm happy to answer any questions during the class time.